Singh, and along with Professor Rita Singh, I built a dataset for audiovisual data, which we call AudioFacialMatrix. This presentation is meant to describe the dataset, talk about some experimental results, and discuss applications of the dataset. So I'm going to be presenting our paper on the AudioFacialMatrix dataset, which is a novel resource that combines audio and visual data to support research in voice and facial imaging AI. This dataset has been developed to address a gap in existing resources and provide insight into the relationship between a person's voice and their facial structure. To start the presentation, here's something to think about. This is an image of a German news reporter speaking, extracted from a YouTube video. And the audio clip that was just played in the background is of another person's voice. Is it obvious that there are two different people apart from the gender? Is it obvious that they're from different nations? What makes this obvious? Let's keep that in mind. So let's go over the agenda for this presentation. I'm going to begin with the introduction. Following that, I'll discuss our research hypothesis that guides the study. Next, I'll dive into an overview of the dataset itself. And then afterward, I'll go over the data collection, pre-processing steps, and then discuss a couple of machine learning experiments briefly, and finally talk about the applications and the implications for this dataset across various fields before wrapping up with the conclusion. So to begin, let's look at the motivation behind this dataset. There's an extensive research indicating connections between a person's voice and their physical characteristics, particularly their facial structure. And this dataset seeks to explore these relationships by providing images and voice recordings paired, organized by nationality across 8 countries. The novelty of the hypothesis, along with the opportunity to produce an expansive dataset and then to explore this data, are some of the main reasons we stayed motivated during this work. Now, this slide represents the core concept behind the AudioFacialMatrix dataset, the connection between the human voice and physical characteristics, particularly facial structure. On the left, we see an illustration of sound waves representing voice. Voice characteristics are shaped by physical structure in the body, like the lungs, vocal cords, and mouth shape, which impact pitch, tone, and resonance of the voice. On the right, we see an anatomical representation highlighting the respiratory and vocal anatomy involved in sound production. These internal structures contribute not only to how a person sounds, but can also have subtle correlations with facial characteristics. For example, the shape of the jaw, mouth, and nasal cavities can influence both vocal properties and external facial features. And our dataset leverages these natural links between anatomy and voice to explore whether there are consistent patterns that could be useful for machine learning models. And by studying these relationships, we aim to support innovations in fields that require understanding or synthesizing voice and facial structure. For our research, the focus is on face structure for visual and anatomical data, and the aim is to identify features in voice data that map to features in face data. As described later, you'll find that although the dataset was created with the intention of identifying such relationships, it has several other applications. Here's a hypothesis. So our research is based on 2 hypotheses. First, there exist distinct groupings based on voice types and facial structures. And second, there's a correlation between these groupings, implying that individuals classified in a particular voice subset are also aligned with a corresponding facial subset. These hypotheses guide our exploration of voice-face associations. Now, this slide explores an interesting question we encountered. What happens with individuals who have identical or very similar face shapes but come from varied geographical backgrounds? In other words, do people with similar face structures, regardless of their origin, have voices that cluster together as well? Well, our experiment results showed that indeed this is true. These faces and voices clustered together, suggesting that there might be underlying anatomical factors influencing both face and voice, even across different geographical backgrounds. Although, with the limited tests conducted on this, it isn't conclusive, but the finding opens up intriguing possibilities for studying universal patterns in human anatomy and voice production. Now, we followed a structured workflow starting with web scraping to collect audio and image data from YouTube, which allowed us to gather a diverse data set. Next, we loaded this data, ensured it was organized effectively for processing. Um, Data cleaning was crucial to remove noise and irrelevant information, followed by separate audio and image processing steps to extract key features like facial landmarks and voice characteristics. Finally, we conducted machine learning experiments to analyze correlations between voice and facial features, supporting our hypothesis about voice-face relationships. Um, this slide outlines the general structure we followed, which is common across many machine learning tasks today. We began with data collection, followed by rigorous data cleaning, and then we processed the signals to extract key features, ran experiments to test our hypothesis, and then refined our models to improve accuracy. This iterative approach helps ensure reliable and meaningful results in machine learning projects. Um, Now, for data collection, we use specific search strings to search for videos on YouTube. This table shows the search strings we use for specific languages. Here, strings such as breaking news were used to retrieve links of videos in specific language. This approach worked well because the native language of a country is most likely spoken by people originating from that country. Um, the next step was to load facial images and their corresponding voice clips from these videos, and the data extraction code was written to ensure that the data was loaded in an organized folder structure. Um, there's more details in the paper about the data set statistics, but here are some of them. And these files have obviously been categorized according to nationality of the individual as well. Um, Now, this slide shows how we used facial landmark detection to identify key features on the face. These landmarks are mapped to specific index ranges, as seen in the code snippet, which which was like written for this. By extracting and analyzing these facial landmarks, we can create meaningful um, features for clustering and comparing faces across different individuals and nationalities. This slide just displays the 68 facial landmark points from OpenCV that we used to detect on each face in our data set. And then this slide is showing you how we use facial features, how facial features can be constructed by connecting specific landmark points on the face and measuring ratios between them. And of course, we just superimposing it on the person's face. Um, Real quick, this table just shows the calculated ratios between various facial landmark points. By measuring and comparing these ratios across individuals, we can identify patterns that help in clustering similar facial structure, supporting our goal of correlating voice and facial data. Um, Now, to identify the most relevant features for our clustering and analysis, we applied several feature selection techniques. First, we used sequential forward selection to iteratively add features that maximize model performance. We also applied DIMNet, which is a dimensionality reduction network tailored for multimodal data to refine feature sets. And we also combined PCA with DSNE, um, setting specific thresholds to retain only the most impactful features. And we experimented with variational autoencoders to see how we can generate compressed informative representations of our data. To evaluate a hypothesis, we ran clustering experiments using facial landmark ratios. We formed clusters that aligned with the 8 nationalities, and the results of these clusters validated our first hypothesis by forming distinct facial groupings based on national origin. For the voice data, we employed liquid time constant recurrent neural networks, or LTNNs, which dynamically adjust their time constants. This adaptability makes them more ideal for audio analysis. Preliminary results showed us that the LTNNs formed clusters for voice data that aligned closely with the facial clusters, hence supporting our second hypothesis. Um, and further description of the results and the experimental setup can be seen in the paper. Now, the audiofacial matrix dataset opens up a variety of applications across several fields. In entertainment, this data could enable realistic voice-to-face reconstruction, allowing digital avatars or characters to be generated based on a person's voice. In communication, the dataset could improve accent adaptation technologies. In forensics, it could be highly valuable for crime investigations. And finally, in medicine, the dataset can support genetic research, helping to identify correlations between facial features, voice, and genetic origin. In conclusion, the audiofacial matrix dataset offers a valuable resource for exploring the link between voice and facial structure. Our experiments provide initial evidence that such relationships can be identified and modeled, paving the way for advanced AI applications that leverage both modalities. That's all for the presentation. Thank you for listening.